Welcome back. In the previous episode, we learned how rising and sinking air changes temperature adiabatically and how lapse rates determine stability. Now we're going further. In this episode, we'll apply those concepts to real-world weather, flight safety, and pre-flight analysis. Let's start with the big picture. As a pilot, understanding stability isn't just for meteorologists. It helps you predict turbulence, cloud types, icing, and visibility changes, all critical for safe decision-making in flight and on the ground. First, let's review how lapse rates are used. You can compare the environmental lapse rate, ELR, to the dry adiabatic lapse rate, DALR, or moist adiabatic lapse rate, MALR. This tells you if the atmosphere is stable, unstable, or conditionally unstable. A steep ELR, like 3 degrees Celsius or more per 1,000 feet, suggests instability. Expect convective cloud development, thermals, and possibly thunderstorms. A shallow ELR less than 1 degree Celsius per 1,000 feet means stability, low clouds, and potential for fog or haze. This is why weather briefings often include upper air temperature profiles. You can use Skew-T diagrams or sounding data to see where inversions, instability, and saturation layers are present. These influence everything from icing to turbulence. Let's take a real-life scenario. You're flying on a summer afternoon. Surface temps are hot, dew point is close, and the lapse rate is steep. As you climb, expect cumulus buildup, bumpy air, and possibly CB development later in the day. Now imagine a winter morning, calm winds, cold surface temps, and a shallow lapse rate. You're likely flying through a stable atmosphere with low clouds, smooth conditions, and potential radiation fog near the ground. Let's connect this to cloud types. Cumuliform clouds form in unstable air, they build vertically and indicate active convection. Stratiform clouds form in stable air, they spread horizontally and often bring drizzle, fog, or steady rain. Cloud height also helps identify stability. A low cloud base with rapid vertical development often indicates unstable air. A high, flat cloud base with broad coverage points to stable or layered air. The visual cues are there, you just have to read them. What about precipitation? Unstable air favors showers and thunderstorms, short but intense. Stable air favors steady rain or drizzle, which can persist for hours. Knowing this helps you anticipate visibility and surface conditions during approach or taxi. Let's talk about icing. Icing risk increases in clouds where temperature is between 0 degrees Celsius and minus 15 degrees Celsius. If the cloud is in a stable layer, the icing tends to be stratiform and widespread. In unstable air, cumulus icing is more localized but potentially more severe. Flight planning tip: always note freezing level, cloud tops, and stability to predict icing zones. For example, icing is more likely near the top of moist, stable clouds, where temperatures fall below freezing but water is still supercooled. Next up, mountain waves and lee-side turbulence. In stable air, when wind flows perpendicular to a mountain range, it's forced upward, then descends down the other side. This sets off oscillations known as mountain waves. Mountain waves can extend hundreds of miles downwind and produce severe turbulence. If the air is moist, these waves may create lenticular clouds, smooth, lens-shaped clouds that form at wave crests. These are visual cues to stay clear. Below the wave, rotors may form, turbulent, rolling air near the surface. These are dangerous, especially for small aircraft. Stable air aloft and strong winds over terrain are red flags for rotor activity and wave turbulence. Now let's talk thermal activity. In unstable air, surface heating causes warm air bubbles to rise, these are thermals. They create bumpy air during the day, especially over dark surfaces like asphalt or farmland. Glider pilots use thermals for lift, but for powered aircraft, they mean moderate turbulence, especially below 10,000 feet. Thermals weaken after sunset, which is why evening flights are often smoother. Next, wind shear. This is a sudden change in wind speed or direction over a short distance. It can happen horizontally or vertically, and is often associated with inversions, frontal zones, or mountain waves, especially in stable air. Pilots should be cautious when temperature and wind charts show sharp gradients. If you're flying through an inversion on departure or approach, expect possible shear. Some modern aircraft have predictive wind shear systems, but not all. How do you use all this during pre-flight? Check upper wind and temperature charts. Look at Skew-T diagrams or soundings if available. Compare forecast lapse rates with actual conditions. Use TAFs, METARs, and SIGMETs to anticipate instability or shear. Let's try another scenario. You're planning a cross-country flight. The TAF shows prob 30 TSRA in the afternoon, and soundings indicate a steep lapse rate with moist air at the surface. That tells you instability is likely. Consider an earlier departure or alternate route. Or imagine you're flying early morning in autumn. Calm, clear night, surface near saturation, and little wind. Expect fog at lower elevations, possibly lifting into low stratus. Stable, smooth air but poor visibility and limited vertical development. You'll also hear the term parcel method in forecasts. This is when meteorologists lift an imaginary parcel of air and compare its temperature to the environment. It helps determine if the air will continue to rise or sink, key for thunderstorm forecasting. And what about tropopause height? If the lapse rate levels off near FL 300 to FL 400, that's your tropopause. Below it, convective clouds can grow. Above it, vertical development usually stops. This affects turbulence and jet stream placement. Here's a pilot tip. If you're flying near the jet stream and lapse rates are steep below it, expect turbulence on the cold side. Knowing this helps you choose the best cruise altitude for comfort and fuel efficiency. Let's recap. Lapse rates tell you if the atmosphere is stable or unstable. Stability affects clouds, turbulence, icing, and visibility. You can forecast stability using soundings, temperature charts, and forecast tools. Thermals, mountain waves, and wind shear are all linked to stability. Knowing atmospheric stability helps you plan safer, smoother flights. In our next episode, we'll begin a new topic, turbulence, part 1. We'll explore the types of turbulence, how they form, and what signs to look for so you can avoid rough air and make smarter decisions in flight. See you in Meteorology number 18, Turbulence, part 1.